scripts that you have to use, the tutorial problems that you have to do, all of them are uploaded on day one in the day one folder. For day two folder, I'll upload the material tomorrow. So that's what we will be using in the afternoon. Perhaps whole of the morning will cover just the basics. So just to talk about the introduction to compilers, what we are essentially going to talk about is the difference between a compiler and an interpreter. So there are two ways of implementing a programming language. When I say implementing a programming language, I mean providing a facility of using a computer for running the programs in the programming language that you have written. So one way is you take a source program and translate it to a target program so that the machine can execute. This is a compiler. So when the machine executes it, you provide the input data. The other way of executing programs is to have an interpreter which essentially takes the program along with the input data, and is the interpreter that runs the program. Runs the program as in it carries out the actions specified in the program and gives you the result. So, so these are the two implementation mechanisms. One is the translation or a compilation, and the other is interpretation. So when we do translation, we perform analysis. Analysis of what? The input program. The input program that has been provided to us, we analyze it and we perform synthesis. Synthesize what? Synthesize a target program. So the idea is you have been given an input program and you're supposed to produce an equivalent, a semantically equivalent target program. So at a very abstract level, this involves analysis followed by synthesis. An interpreter, on the other hand, theoretically speaking, a pure interpreter performs analysis and performs execution. It does not perform any synthesis. However, all practical interpreters synthesize some internal form of the program and then execute it. So this is the basic difference. I want to begin by showing you the basic difference between compiler and interpreter, because this is one of the questions that people have, and the best way to do that is to actually take a demo. So I have a demo program here. So I'll just go to the same directories have been given to you on the Google Drive. So let's go to demo of compiler and interpreter. Yes, so I can just recompile. LP is language processor. I have some input text. What is it that I want to do? So there's an input text which is, all of you are able to see it? Is the font size okay? Do you want it bigger? Is fine? So we have two assignment statements. The first statement says A is equal to 10 plus 20 star 30, and the second assignment statement says B is equal to A plus 10. Now we want to see what is the difference between compilation and interpretation. So if I were to run /lp less than input.txt, we get what we call as a 3-address code, where each intermediate expression is stored in a new temporary variable. Okay, so we will see 3-address code generated by practical compilers today later in the afternoon. But this is the way. So this compiler is very simple. It takes a sequence of assignment statements and converts them into 3-address code. So this is the equivalent 3-address code. As you can see, we have stored 20 into 30 into T0 because multiplication has a higher precedence than addition. And then we said T1 is equal to 10 plus T0. And then we said A is equal to T1. So this is an equivalent program. This is what a compiler is supposed to do. Now I can tell if I were to say minus help, these are the options. So minus C is the default option, which is to compile it. Minus I is to interpret it and print the result. So if I were to repeat the same thing, LP input.text, but now for a change, I say interpret it. Now it has done something else. It has printed the values of variables. This is interpretation. We are not giving out an equivalent program. Instead, we are performing the actions implied by the statements and are printing the way, let's proceed. May I please request silence? I can't tell you in Tamil, I'm sorry, but yeah. So, so another way of looking at implementation mechanisms is to see them as bridges. So we have a program specification which is at a higher level, and we have a machine which is at lower level. When we say higher and lower, there is no value judgment here. It's only the amount of detail. At the higher level, we have fewer details, and at the lower level, we have many details. So what a compiler does is, what a translator does is, takes a source program and lowers the level of specification to the level of machine by bringing in progressively more and more details. On the other hand, what an interpreter does is it raises the level of the execution of the program to the execution of the program to the level of the program. Raises the level of the execution from the machine to the level of the program. So there are two ways, these are two fundamental ways of bridging the gap. Levels can be described as, at the higher level, for program specification, we can see a program as a state machine where state is defined by the values of variables, and operations that cause state change are the assignments and control flow. At the lower level, the same thing can be described as a state machine where now state is defined by the values in registers and memory location, and operations are machine instructions. Just to see the difference between lower and higher level, here is a C++ program, a high level specification. It just computes the factorial of a given number. All of us understand what the program does, but our goal here is not to understand what the program does, but to understand what we can do with the program as a compiler. That's the goal that we have. So this is a higher level. Now, what do I mean by lower level? This is the lower level representation. Okay, this is just one page, another page, and third page. So two pages. So this is the difference. This is the high level representation, and this is a low level representation. So a compiler is supposed to take us from this level to this level. So my slides have given commands on how you can generate it. You can try and play with the programs that you want to look at. Okay, so let us now look at slightly greater details of lower level to high level, and after a few slides we will go back to how to. So we will take this statement. What does the input statement mean? The statement says if b is less than 10, then assign the value. If b is less than 10, then assign the value of b to a. Otherwise, assign the value of c plus 5 to a. It's a ternary expression in C. I presume all of you understand it. Is anyone here someone who doesn't know what a ternary expression means? Please raise your hands. Excellent. So all of us know what this means. So conditionally assign the value of b to a or c plus 5 to a, depending upon the result of the expression b less than 10. And here is SPIM assembly equivalent. SPIM is a MIPS simulator, MIPS spelled backwards. SPIM is a MIPS simulator, which is what we use in compiler construction course at IIT Bombay. So this is a simulator, and this is the lower level representation. So you can see what it says is load the value of b in a register v0, then compare v0 with 10, then for some reason negate it, and if this result is something, go to label L0, where at L0 we will load C, then add 5 to it and store it at A. So so you can see at the higher level we don't have registers, we don't have control transfers, we don't have the notion of actual checking and transferring the control. But at the lower level, all this comes up. So we have to see how to translate this statement into the lower level representation. Okay, so let's ignore some details. So that, as I said, there are two broad models of language implementation. We have analysis followed by synthesis, which is compilation, and we have analysis followed by execution, which is interpretation. Okay, practically what happens is, and this is what practically happens. sorry, I'm very intolerant of distractions. Okay, so practically what happens is between a front end and a back end, there is an optimizer sitting in between. And when we have a back end, which is what performs the analysis, front end is what performs the analysis. Back end is what performs the synthesis, front end is what performs the analysis, and optimizer transforms the intermediate representation to make it more efficient. On the other hand, we might have virtual machines. So backend is there in compiler, so we is used by languages like C and C++. And then you have virtual machine which executes an intermediate representation. So this is the interpretation branch which is used by Java and C Sharp. So in case of Java, the front end and optimization will be there in this command called javac, which is a Java compiler, which produces a bytecode, and then bytecode is executed on JVM, which is a virtual machine. Okay. There are some arguments about why do we need compilers and interpreters both, about the timing, etc. But again, let's not get into too many details. The details are here, and you can look at it, and we can discuss it offline. The whole idea is that interpretation overheads, if you have to run the program multiple times, and interpretation overheads are high, and you can go for compiler. And you can even do what is called JIT compiler, just in time compilation, which essentially saves the interpretation overheads. So, so the idea behind providing a language implementation is to be able to reuse the modules of a mechanism as much as possible. So we might have several front ends, and we might have a common intermediate representation, and we could have several backends and virtual machines. So as you can see, the common IR is what forms the basis of one front end talking to a backend or a virtual machine. So this intermediate representation becomes the most important part of a compiler. In fact, as it turns out, unfortunately, the standard textbooks on compilers, including Ahoseti and Ullman, they essentially abstract out things so much that intermediate representation becomes incidental. But if you talk to any practitioner, you will realize that the design of the intermediate representation is the most crucial aspect of a compiler. Everything else depends on the IR that you design. Okay, so we are going to look at simple form of intermediate representations today. Okay, so let's get back to the overview of compilation phases. So we want to see a journey of a source program to an assembly program. Of course, when we say a compiler, it produces assembly program, and then invokes an assembler, then invokes a linker to give us an executable file. But for all practical purposes, we are going to look at generation of assembly program as the main goal of compiler. There are other tools that will add to the tool chain and will provide final executable. So we want to look at this, and what we want to do is we want to look at the structure of a compiler. So we have a scanner, which is essentially something that reads the program, reads the program character by character, groups the related letters together to identify that this is a keyword, this is a variable name, this is a number, this is an assignment statement, this is assignment operator, this is the plus operator, etc. So that's a scanner. And then there is a parser. So scanner produces what are called as tokens. Tokens represent the smallest indivisible unit in a program. So when you write a variable called count, you do not want the compiler to treat C as separate from O, as separate from U, O, and N and T. You want the compiler to see all of it as one single unit without dividing it any further. So it's a scanner which does the job of identifying the smallest unit in terms of tokens, and the parser identifies relationships between different tokens, and it calls something called a semantic analyzer. So scanner will tell us whether the program has made any lexical errors, has there analyzer finds out whether the program has the right meaning as assigned by the language to any given program. So then there is an IR generator. So parser gives an abstract syntax tree. We will see examples of all these in a short while from now. And then we have a 3 address code, and then which is given to an instruction selector, which finds out instructions, decides which registers to use, and finally it generates what is called register transfer language. This is a scheme of a compiler. There can be many other ways of organizing a compiler. We are going to look at one of the simplest ways, and from that we get an assembly program. So as you can see, there are multiple passes here. So there is one pass which is the parser. So let's assume all of this is one single pass. This is the next pass, this is the third pass, and this is the fourth pass, right? So this compiler has 4 passes. Does anyone know how many passes does GCC have? Any guesses? There are no marks, so you can guess wildly. Any guesses? What do you expect? What do you anticipate? Hey, come on, you have to speak up. How will I know you're not sleeping? You don't speak up. Yes, someone wants to hazard a guess other than Professor Krishna? No guess? 8 to 5 or 6? 8 is another number. Any other number? 20. Okay. Since I'm asking, obviously you will think that we need a bigger number. So I'll continue to ask. Any other guess? 50 to 60? Okay. Any other guess? Well, the real answer is GCC has more than 350 passes. 357 to be precise when I looked at the structure. I'm counting. The reason why I'm saying this is this should increase your respect for the compiler writers a little bit. So when you compile just a program, hello world, this is the kind of work that GCC has to do, right? So real compilers have so many different passes. And why do we have so many different passes? The idea is to lower the level of abstraction from high level to the low level in smaller steps. Is it better now? Uh, yeah. So now is it better? Yeah. 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 Okay. So, so GCC has, so the point is we have to have, it's very useful to have a larger number of passes because then every pass can do one small thing but do it well enough and do it efficiently. So the idea is to divide the work in many small steps such that each step can become more and more intelligent. That's the reason why compilers have a very large, practical compilers have a very large number of passes. Okay, so let's go by this structure. This is a structure that my students have to use in implementing the compiler for the UG compiler construction course. So we are going to look at this all the intermediate representations beginning from the source statement. Here we have this input statement. We just saw it before. A is equal to B less than 10. If so, assign the value of B to A. Otherwise, assign the value of C plus 5 to A, right? So, the first part of the compiler is to perform parsing, which internally calls a scanner. So, what does this show? This shows that the input, so this input statement is actually stored in the memory like this. We have A followed by a space, followed by equal this is what is tokenization. So once we get this, as you can see, these are the things that represent leaf nodes of this particular structure. It's a tree. And what does this tree says? This tree says that what we have is an assignment statement, and an assignment statement has a left hand side, an assignment operator in between, and an expression on the right hand side, and is followed by a semicolon. So we're trying to find out the structure of the input statement. Okay, and we say this LHS, left hand side, incidentally happens to be just a name, and that's a leaf node in this tree. This tree is what is called a parse tree. This tree is what is called a syntax tree. This represents the syntax of the program. Okay, so we have left hand side as just a name, right hand side is an expression which happens to be a ternary expression. And how does it, what is the structure of a ternary expression? A ternary expression has a condition, and which is an expression, followed by a question mark, followed by an expression which represents the true part of the expression, and an expression which represents the false part of the expression. So we have this condition which is also an expression which happens to be a comparison expression. Again, we are comparing two expressions, A less than A, and this A happens to be name. Why is it name? Because it represents the B. And this A is a number, which is this number 10. Okay, and this true expression happens to be just a name, which is just a variable B, and the false expression happens to be a plus expression, which is again expression plus expression, and this expression happens to be a name, and this expression happens to be a number. Okay, so a parser has to deal with grammar rules. A parser has to deal with terminals and non-terminals. How many of you have studied context-free grammars in some course in computation? Are you aware of that? Okay, several of you know, several of you do not know. So context-free grammar is a way of describing the structure of a language, and we can use that grammar to specify how different sentences in that language should be derived, and we can have a tool which can check the structure. We can have a recognizer which tells us whether a given sequence follows this structure or not. And a parser is exactly that recognizer. So the input to a parser is a specification of the grammar, which is essentially, which gives us a structure, and a parser creates this parse tree. The internal nodes in the parse tree are what are called non-terminals, and the leaf nodes are what are called terminals. So terminals are the symbols where derivation of a parse tree terminates. You can't derive it further. You can't have any more children for that node. And non-terminals are the nodes which would have some parse tree nodes until we reach a terminal symbol in the tree. And the terminal symbols of a parse tree are exactly the tokens that a scanner has identified in the program. And of course, the parser has to worry about many things. For example, we have written this statement. Implicitly, we are saying that this is A is equal to some expression. How do we know that we do not have to group A less than A is equal to B less than 10 as one thing, followed by B colon C? How do we know that? So intuitively we know that language is specifying it, but a parser is supposed to know it formally, a parser is supposed to know it rigorously, and a parser will never go for this division. Parser will never, if a parser has been written correctly, a parser will never go for this grouping. So a parser has to identify what is the right relationship. Technically speaking, there can be many relationships, many groupings of tokens, and a parser has to identify what is the right relationship, what is the right grouping, and how does it know it? It knows it because we have specified the grammar. The grammar tells us how tokens have to be grouped together. Okay, so this is the parsing, and we will see examples of parsing as well. And now look at the next phase, which is semantic analysis. So semantic analysis takes parse tree as an input and tries to assign meanings to various nodes in the parse tree, various elements in the parse tree, and it's supposed to create what we call an abstract syntax tree. So what we have in yellow is a syntax tree, or to be more precise, a concrete syntax tree. What we have in blue is another syntax tree, but it's an abstract syntax tree. It's abstract because various things that were required primarily to group the tokens have been buttered off, and we retain only the important things that tell us what the structure of the input is. We have already identified that it follows the right structure. Now we'll get rid of whatever is not required. So now here we say this is an assignment statement which has a left hand side and a right hand side. Left hand side happens to be a name, and we are associating types with the name. So we are saying this name happens to be A and its type happens to be integer. So this information has been stored in the symbol table where we have stored the names of the variables and their types. Right hand side is a ternary expression whose type is integer, and this ternary expression has a less than condition, a comparison condition, and it has this expression and it has this the false expression. This ternary expression, a comparison expression, has a name followed by a name. So we have to worry about the names in the symbol tables. We ask a question, have the variables been declared? What are their types? So these are the pieces of information that are stored in a symbol table. Are the variables in the current scope? And then a semantic analyzer primarily checks for type consistency. A semantic analyzer says that yes, you have used a plus, so therefore the operands of plus have to be either integer or floating point. They can't be strings, for example, or you can't use a keyword there. Okay, so this is an abstract syntax tree, and the types are stored as attributes. There can be many different kinds of attributes. What do we mean by attributes? The properties of the nodes appearing in the abstract syntax tree. So this is an abstract syntax tree. Now you can see that given the statement, you can easily relate it to the yellow box. We don't want to get into the algorithm to identify yellow box. We want to understand intuitively that what has been given in yellow box indeed corresponds to the given input statement in pink, and whatever has been given in yellow box corresponds to, or whatever has been given in the blue box is obtained from what is there in the yellow box. Are you all able to see the correspondence between them? Are you all able to see how does this represent this and how does this represent this? Before I go any further, I would like to stop here and take questions if you have any about the correspondence of how blue represents what's there in yellow and how yellow represents what's there in pink. Any questions? You should ask questions. Not for you, but for me, so that I get some rest in speaking. Yeah? Any questions? Symbol table is a structure where we store some information that we have derived from processing the declarations. So we will have variables, their types, and the scope information. And are they local variables? Are they global variables? So we somehow store the scope information which region of the program is it confined to. This is the primary purpose of symbol table. Later, we will assign stack offsets. When we assign space to these variables in the memory, they may go on the stack or they may go in the static memory. So we will assign addresses to these variables. Later phases will assign addresses. So in a nutshell, symbol table is a table containing symbols appearing in the program and their properties, their attributes, and their information. Yeah. Any other question? Is the correspondence let's go further. Yeah. Yeah. So we have here the symbols and their types, or we have expressions and their types. So every entity in the abstract syntax tree has an associated type. Statements do not have type, but expressions have types and variables have types. So for example, observe here that is the type of this expression is a boolean. The result of comparison is not integer. Result of comparison is either true or false. Result of comparison is not 5 or 6. Right? It's true. It may be represented as a zero or non-zero value, but technically speaking, it's a boolean value, true or false. Whereas this expression has an integer value. Right? So these are the attributes of the variables or the expressions occurring in the given input state. Yeah, shall we proceed? Yeah. If we have to, scope of the variable is specified by where it is declared in the program. Okay, so if a declaration is a part of what we call as a compound statement in C or C++ languages or even in Java, you have a pair of braces giving a compound statement. If you give a declaration there, the scope of the variable is restricted to those pair of braces. Good question. The question is, how do we define the scope of a variable in a symbol table? Uh, yes, the natural question is, will we write scope 1, scope 2, scope 3? That's very confusing. So the way symbol table organized is, if you if you have carefully seen C, Java programs, you see that a compound statement can contain another compound statement. Every procedure or every function itself is a compound statement. And then it contains another compound statement. And that may contain another compound statement. Right? This relationship in a symbol table is stored in as a stack of different entries. So innermost symbol table, innermost compound statement is the top element in the stack. Below that is the outer compound statement. Below that is the outer compound statement. And at the lowest level, we have the global entries. So when we have to search for the whether a variable is in the current scope or not, we start searching for from the top of the stack. Whichever entry we find is the current variable in scope. If you don't find it in the scope, then we go down. If you don't find it in that entry in the symbol table, we further go down. Eventually, and that's how local variables supersede global variables. So eventually, we will find it as a global variable. And if we don't find it, then the compiler will complain that this variable has not been declared. Does that answer your question? Data structure of a symbol table is a stack. Data structure of a symbol table is a stack, and the lowest entry of the stack is the global variables. Then we have the outermost level within a procedure. Then we have inner levels, etc. So it is a stack and it keeps changing as we process different parts of a procedure. Yeah, good. I'm glad you're asking questions. Any other question? Any further question? You should not let me proceed if there is something that's not clear to you. There's nothing like, I don't know how to ask this question. What will people think? People think nothing. They are worried about their own question. They are not here to think about you. Okay, so don't worry. There's no question is a stupid question. Every question adds value to these sessions. We want to keep these sessions as interactive as possible. My goal here is not to be a sage on the stage, but my goal here is to be somebody who helps you understand things. And the more you ask, the easier it is for me to reach you. My goal here is to reach your mind and heart. So this is fine. Now what happens here is that, as you can see, let's say you take abstract syntax tree. Can you implement it on a practical machine? All of you have done some assembly language programming, you have seen. Uh, so do you have an instruction in one of the machines which says how to implement ternary expression? Machine has lower level details. A machine doesn't have the higher level structure which says select this block of code or select that block of code. We have to arrange the code in such a way that a machine can understand it. So we have to explicate the control flow. There's an implied control flow here. What is the implied control flow? The implied control flow is with an expression. Depending upon the result of the expression, either we want to evaluate this or we want to evaluate that. Right? So we have to explicate it so the machine can understand it. So therefore, what we do is we flatten this tree. We traverse this tree and linearize this tree and come up with a representation which we call as a tree address code representation. Now, we can visualize a machine taking each statement one by one and executing it. For example, here we are storing T1 is equal to B less than 10. So we will first evaluate this. We will first check if B is less than 10. And then for whatever reason it negates it. The idea is to have the true branch first. So then he says if T2 go to L0. What does T2 represent? T2 represents negation of B less than B less than 10, which means that if B is not less than 10, then go to L0. Which means that if B is actually less than 10, in which case T2 will be false, the control will be transferred here. So if B is less than 10, control this will be false and we will have the result of B stored in T3. On the other hand, if B less than 10 is false, so its negation will be true, and because its negation will be true, control will be transferred to the label L0, which says add C and 5 and store the result in T3. Note that in either case, we are storing the result in a variable called T3. Okay, and then eventually, then there will be a fall through, and then we will assign T3 to variable A. Can you see how the gray box is obtained from the blue box? Can you see why what is there in the gray box corresponds to what is there in the blue box? If you have any question, we should stop here and we should talk about it, because this is exactly what you have to do today in the afternoon. Today you will observe how Clang and GCC give this piece of information. So in order for you to make sense of what the practical compilers do, first you have to understand what the concept is here. And here we have taken a very simple example, and I am willing to repeat it multiple times if you have any questions. I want all of you to be with me. I don't want anyone to be left behind in this journey. Any questions? Does it make sense? Yes. Yes. But, yeah. Yeah. The question is, complete the question, then I'll repeat the question. Yes. Okay, the question is that we are linearizing the tree by going from bottom to top. Can't we do the linearization by going from top to bottom? That's the question. And the proposal is, can we have A is equal to 3 in the beginning? Is that what you're trying to say? Yes. Right. Why? Very good question. Very good observation. When we look at the program, we are reading from left to right. But, so leftmost symbol is A, whereas this symbol appears here in the end. Whereas here we read A as the first symbol. Very good observation. Is there a problem there? Very good observation. Why do you think there is this inconsistency? Somewhere A is the first symbol and here you're saying it is, I'll worry about A in the end. Can someone tell me? Does it make sense? If yes, why? Yes. The semantics of an assignment statement is that the right hand side is evaluated before putting the result in the left hand side. So we have to evaluate the expression on the right hand side and then store the result in the left hand side. So that is the reason the right hand side subtree has to be evaluated first, and that's the reason why we have to do is we have to worry about this first. And when we worry about this first, the first thing that we have is this comparison operation, which is what we are doing here. So it's not even exactly top down, bottom up. It's some form of, so the goal is first to generate code for this expression in order to, so we start by the way it recursively works is we start by generating code for this. Now we know that we have something here, but we have to generate code for this. Now in order to generate code for this, first we have to generate code for this, then we have to generate code for this, and then we have to generate code for this. So actually we are traversing the tree, abstract syntax tree, top down. But the first piece of code that is generated is for the node whose leaf we hit first. So, or whose all leaves are hit first. So for this, we haven't really done anything for this. So therefore, no code will be generated for this. But when we come here, these two leaves, we have read this, and therefore, this is the part whose code will be generated first. That's a very good observation. Are you able to relate the order? Yeah? Any other question? Please let the questions keep coming. Grammar will tell us how things are to be grouped. Okay? The semantics of the language will tell us in this grouping what should be done first. In fact, crazy situations arise when we have plus plus operators sitting here. Okay, and then there are gory details of how plus plus should be evaluated. I mean, I often give that question in my mid-semester examination. With a plus plus, what will be the abstract syntax tree and what will be the result and why? Okay, so yes, so there are two things. Grammar gives the structure, and then there is semantics specified informally in the language definition documents, which has to be encoded by a compiler. Good question. The question is, what if a certain operator has multiple meanings, multiple effects? For example, plus can be used for addition of numbers, integer or floating point, or plus can also be used for concatenation. This is where the type information comes in handy. So we can say that an operator has multiple meanings. How do we find out which meaning is implied? By looking at the types of the operands. If the operands of plus are numbers, then we know we are doing addition. If the operands of plus are two strings, then we know we are doing concatenation. Right? But if the operand of a plus is one is an integer and the other is a string, then it depends on what the language says. For example, in Python or in R, the language will say treat them as strings. Treat the number also as string and concatenate them. Or language like C++ will say no, I don't allow this. So that will get type error. So this is governed by the semantics of the language. Yeah. Any other question? So far all of you with me? Okay, so now that we have seen, now I want you to keep in mind that we have this journey from this assignment statement to parse tree to abstract syntax tree to three address code. Tag stands for three address code. Now we can actually perform instruction selection. Okay, so we can say, so this is called RTL. RTL is Register Transfer Language. That's a name that people use to indicate statements, and we RTL visualizes all computations as transfers from one register value into the other register value. So as you can see here, this magenta box corresponds to this gray box, which corresponds to this blue box, which corresponds to this yellow box, which corresponds to this pink box. Okay, so in the magenta box, what is the difference between this and this? Here now we have included the machine instructions, the actual instructions that my architecture provides. So for example, if I have T1 is equal to B less than 10, I can't do that directly on my MIPS machine. What I have to do is I have to load the value of B into V0. Okay, then I have to use this instruction SLTI. SLTI stands for set less than, and I is for immediate. So one of the operands is immediate. So if 10 is small, if V is smaller than 10 and 10 is an immediate operand, so there is a register and an operand, and this is an immediate operand. So store the value in T1, and then we do not of T2, not of T1. Not is not directly information available on MIPS. We are just encoding it. There's something else that we have to use. So we negate it, and then once again, if this is something, if this is true, go to L0, otherwise go to L1. And at L0 we are doing T3 is equal to C plus 5. So we load C in T4, and then we add 5 to T4 and store the result in T3. And then finally we store the result in A. This is what will be happening at the lower level. So you can easily see how does this correspond to this. Now the beauty of compiling is, we've been talking about this, but we haven't got into the details of the algorithm at all. This is an approach which we call as the gray box probing. You may have heard of things called black box and white box probing. A black box probing says that look at everything in a black box, just relate input to output. And white box probing says open up everything. We are doing something else. We are not opening up all the phases. In fact, we are opening up just at the intermediate phases. So we call this as the gray box probing. This is the best way of understanding a compiler before getting into the algorithms of the compiler, because your mind intuitively can understand what is happening. Your mind can tell you, yes, these things correspond. Once you understand this, then there is a step of how do we obtain these structures, right? But we are going to focus on gray box probing of compilers today. Once we have RTL list, then we generate the assembly code. And when we generate the assembly code, we have offsets of variables in the stack frame. In the symbol table, these addresses will be stored, and then we will have actual register coming in. So for example, B is an offset at an offset of 4 from the frame pointer, and then we have this. So all these, now we have added offsets, actual register names, and assembly mnemonics. So here we don't have a NOT, so we use exclusive or XOR instruction, and this is how we generate the code. So this is the translation of this input statement into this assembly code, right? And we go from each step, and the idea here is to understand each step intuitively. So I will pause here and take questions. Yeah, question? So are you able to see this incremental transition, incremental step? So each of these is an intermediate representation. This parse tree is an intermediate representation. This ASP is an intermediate representation. This three address code is an intermediate representation. Then we have RTL, and then we have the assembly code. Right? If this was clear to you, I'll give you a small demo. We have another 5-7 minutes before we have to break at the scheduled time. So we'll worry about this later. Let's just come to this. Demo of SCLP. So this executable has been given to you on the Google Drive. It's been compiled on Ubuntu 24.04. If your laptop has that, you should be able to run it. Otherwise, you may not be able to run it. I have not given you the source code, obviously, because my students are supposed to write it, and I don't want source code to leak. So I will. So there is a README file associated with this, which you can see if you are able to run it. Cat README. Okay. So there are details of the language, but let me just run this dot slash L5 SCLP minus minus help. Oh, these are all the options available to this particular compiler. So we can stop after scanning, parsing, AST or 3 underscore or RTL. We can say show tokens, we can say show AST, show tag, show RTL. So let's observe the tokens. So we have some examples in level 5 test cases. So let me just run L5 SCLP and minus D is for demo version, which prints on the screen, and minus minus show tokens less than uh, level 5 test cases. And let's pick up some example 1 dot C, and I just pipe it to less. Oh, what happened? I don't have this, is it? I give the name, is it? Yeah. So these are the tokens. So it says token name void, lexeme void, line number. We'll look at the details of these tokens after the break. Okay. So these are all tokens that are produced. Okay. So let's just look at the program. So cat L5 cat level L5 test cases L5 EXMP. Why is it? Oh, small m. Okay. EXMP1.c. So this is a program. We just say void f int a is equal to 5, void g int b, void main, call f and call g. Simple program. So for which the tokens are produced like this. Now I may want to see what is the abstract syntax tree. So instead of show tokens, I can say show AST. Okay, and it shows this abstract syntax tree. It shows the symbol table, it shows the types. Return type is void, there's no formal parameter, begin abstract syntax tree, it's an assignment statement, then this procedure G, etc. All this. In the afternoon, what you want to do is, let me just quickly show you that CD visualization. So I can just say sh draw parse3.sh sample program. These are C programs. Let's just say add.c. Oh, I have not initialized Clang. Okay. I thought I had installed Clang. Okay, let me just show you the CNG. Draw CNG. So it has produced this control flow graph, and then I can view it with x dot. I don't have x dot as well. Okay, looks like on this laptop I thought I had. Okay, I'll just install it and we'll check it in the afternoon, right? But I can right now do dot minus t pdf and dot c dot dot minus o and dot cng dot. I hope this works. Yes, and now I can see and dot c dot. So this is the control flow graph whose details we will see. I'll also show you how to get abstract syntax tree after the break. Yeah. So I will stop here for the break. 10:30 is our time for the break. We'll resume at 11 o'clock. I want you to discuss with each other. I want you to ask questions to us. I like to be around the students during the break, so please feel free to ask questions. And we'll stop here and we'll resume the lecture at 11 o'clock. Yeah. One of the problems in such workshops and winter school is we break for the tea and we realize tea has not arrived. So somebody has to confirm whether the tea has arrived, whether we can. So in the meanwhile, sudo apt install client. Tea has come? Yeah. Okay. Sudo apt. Yeah. Okay. I don't have the internet. Yeah.
There's a short break for tea. You can have tea and snacks outside the hall.